we don't have. Bismillah ar-Rahman ar-Rahim. I think we should start. I know people are still having lunch, but we have 1.5 hours to, so we have to end by, what is it? Yeah, we have to end by 3:30. And that's why I think we need to start. So, yeah, people will be coming during the session, but that's fine. Well, welcome to this session. As you know, we've been in this room for FAO since the morning. So we've had 2 previous sessions, and this is the 3rd. And this session is going to discuss climate change impacts on water consumption and water productivity of crops, update and recent findings. Basically, what we're aiming to do is put science into the picture. So we want to inform you what is the latest in terms of models, predictions that connects the issue of water scarcity to crop production. And given that climate change has an impact, and we also, for those who are doubting, we saw last summer, not only in this region, we see it every summer in this region, but in Europe and elsewhere where water is more available. This past summer was really not pleasant for them. Extended droughts, restrictions on water use, and on the other hand, we saw in Pakistan very heavy flooding, disastrous, etc. So climate change is here and maybe happening at a faster pace than we originally anticipated. So this is going to be an issue we need to cater for, we need to address, and in order to cater for it, we need to see how that impacts agricultural water use. And in order to do that, we need to see what the science is bringing us. I'm very pleased to announce that we have leading experts on this topic to enlighten us and explain to us how is this going to affect production, productivity, and what I would say, water scarcity and the growing water scarcity due to climate impacts. So I'm not going to take more time. I'll give the floor to Muhammad, my colleague Muhammad Abdullah. He's moderating the session. He's introducing the speakers. So over to you, Muhammad. We can start. Just to mention that at the end of the session, we're also pre-launching a report on the certainty and the connection. Actually, remote sensing determination of evapotranspiration, looking at the different alternative options that are available and the error and uncertainty connected to it. We have our friend Pasquale Istituto. He's connecting from America, California, and he will be presenting this report, which will be launched later in the year. Thank you, and over to you, Muhammad.
Muhammad, this is a bit challenging because we started 20 minutes late than the scheduled time, but I would like to thank our participants and our distinguished guests. We have 2 distinguished guests who will be speaking virtually, and we have our distinguished guests here also in the room. So I'll begin with the first speaker, Dr. Elias Freires. His professional area of expertise is centered on the sustainability of water-limited agriculture and the role of water in agriculture and the environment. He's currently an emeritus professor in the School of Agriculture and Forestry Engineering in the University of Cordoba in Spain, and he's a researcher at the Institute of Sustainable Agriculture, Scientific Research Council of Spain. He's also a member of the Royal Academy of Engineering of Spain and of the Academia Europea. His most recent work deals with the assessment of water productivity in the Middle East and North Africa in a project with the FAO. So, Dr. Freires, the floor is yours. Please share your presentation, and we are all listening to your presentation. Thank you.
Thank you very much to all the organizers for inviting me. I am sorry not being physically with you, and I wish hopefully in future seasons. Thanks very much, Mr. Chairman. I'm going to start sharing the screen. Okay, the title of my presentation is Predicting Climate Change Effects on Irrigation Water Requirements, which I have done with my colleague, Margarita Garcia Vila. Well, we know that irrigation requirements come from two components: the consumptive use of the crop, which is one entity, and the other entity that contributes to that evapotranspiration is effective rainfall, the amount of rainfall that contributes to evapotranspiration. So the net irrigation requirements, and by net I mean we do not compute the losses due to runoff or percolation or problems in the system, but just the difference between the crop evapotranspiration and the effective rainfall. And we know that crop evapotranspiration is normally determined as a product of two factors. One is the evaporative demand quantified as ETO of the evapotranspiration of a short grass crop, and a crop coefficient that converts that reference evapotranspiration to the crop evapotranspiration. So for the topic today, we need to assess what are the impacts of the climate change that we are already experienced, as Dr. Alhamdi indicated, on precipitation, evapotranspiration, and crop coefficient, reference evapotranspiration and the crop coefficient. If we start with precipitation, I am offering you a record of 120 years of annual rainfall at the location where I am, southern Spain, in Andalusia, Spain. And you can see the variability from year to year that is tremendous. The range of variation goes 4 times. There are years of 1200 millimeters and years of 300 millimeters. It's difficult to see any pattern that is not a random occurrence of annual rainfall. There is one feature, though, is that there are many more years below the average than above the average. This is characteristic of the semi-arid environments, but it's very hard to conclude anything from the records of effective precipitation. Two issues emerge: the variability that I have mentioned from year to year, and now relative to climatic change, there have been efforts by modelers to predict the future rainfall in future climates. And when there is a lot of efforts now in developing regional hydrologic models for future precipitation prediction. But these predictions are still very uncertain, and there is a community of hydrologists that are highly skeptical as compared to predictions of increasing temperature, which are not only certain, but that we are already experiencing. So we have a lot of uncertainty in predicting the rainfall for the future. There are areas in the world where we see that it's declining, in other places it's going up, but these trends cannot be deducted from past records, because in most places the past records are 1 to 200 years, not sufficient to give a real clear-cut picture of what will happen in the future. There has been advances in predicting regional precipitation in some parts of the world, by especially those that are affected by the phenomenon called El Niño Southern Oscillation, like Australia, South America, and some parts of East Africa. But other regions of the world, there's no way to predict medium-term precipitation. Now, what about a reference evapotranspiration? Is it as variable as rainfall? The answer is no. There is much less variability in annual evapotranspiration, the reference evapotranspiration, than there is in rainfall. You can see here 65 years of records in Córdoba, where you don't really see much of a trend of should be going up, but slightly going up in recent years that have been associated with very dry years, but you don't see much of a trend. However, if you plot the same data relative to the annual average temperature, so you plot every year against its own annual temperature, you see an increasing trend as the temperature increases, to the point that there is a reference ETO increase of about 4% per degree C increase in temperature. So this is one way of looking at it. There seems to be an increase in ETO empirically with these records, but we can also do a calculation looking at the relation between average temperature and reference ETO using the Penman-Monteith equation, which is an equation that FAO uses to calculate reference ET. And considering that solar radiation is the dominant factor in this equation, the role of temperature can be deducted by increasing it artificially. So I did an exercise for Cairo. First, I calculated the ETO, and then I increased every week the temperature, the mean temperature, by 0.5 degrees in steps. Starting at 1 degree increase, the results indicate that the ETO, reference ET, increases by 5.6%. And when the average temperature goes up 2 degrees, it's 11.3, and if it's 3 degrees, it would be 16.9% more. So this is the theoretical increase. If only temperature will change 1, 2, or 3 degrees, then you will have an increase in reference ET as calculated by the Penman-Monteith equation of about 5 to 6%, exactly 5.6%. Now, there have been other efforts to determine the increase in reference ET in the region. I found this article entitled "Impact of Climate Change on Reference Evapotranspiration in Egypt," published in Catena, a soils journal. They took a record of 34 years, divided into two parts, 17 years before the end of last century and the first 17 years of this century. They calculated the ETO according to Penman-Monteith for the two regions, and they took the difference. The difference shows that the ETO has gone up substantially. In some areas, 300 or 350 millimeters. These are based on the calculations for very short time series. 17 years is not long enough to give any trend. And if you look at the at the difference in ETO between the two periods, and I read it from the graph because there are no data, numerical data in the paper, but it seems an exaggeration of the increase in ETO. It gives an increase of ETO in 17 years of for 9%, which would suggest an increase in temperature much higher than has been measured in the long-term trend of temperatures in the region. So there are efforts, but in general we can say that on one hand, future rainfall is largely unpredictable. Reference evapotranspiration will increase, but there are other factors in play. I will point out to one, and that is that the increase in temperature makes the development of the crop faster. If the crop develops faster, the growing cycle would be shorter, and there will be less time from sowing to harvest. In this shorter duration of the crop, even if the ETO is higher, will lead to lower ETO because the season is shorter. So this goes against the increase of ETO the temperature will affect. The balance between the two, the increase in ETO for a higher temperature and the lower ETO for shorter season, will result probably in somewhat of an increase in ETO, but less. Depends on the crop. But the crop also affects another factor, which is the crop coefficient. And the crop coefficient is regulated by another component of the climate change, which is the emissions of CO2. The increase in CO2 concentration is known to produce partial stomatal closure on crops. So the leaves will close stomata when the CO2 concentration increase as a result of climate change. Remember that the warming is being produced by the emissions of CO2. All those simulations that shows warming without CO2 makes no sense, because the cause of warming is an increase in CO2. So CO2 is going up as the temperature is going up. So the question is, if the stomates of the leaves close, how would a reduction in the conductance of the stomatal conductance of a leaf, which is the degree of opening, will affect the transpiration of the canopy, of the whole canopy? Now, to respond to that, the answer is not yes or no, but the answer is that it depends. Because depending on the type of crop, the closure of a stomata will produce more or less reduction in canopy transpiration. This is based on a complicated theory that I have no time to cover, but I will summarize it in the next slide by saying that the response of the crop to a stomatal closure in terms of transpiration depends on how much the crop is coupled to the atmosphere. In general, smooth crops, short crops, are poorly coupled to the atmosphere, and this is regulated by, and this theory was proposed by Jarvis and McNaughton in 1986, and they define a degree of coupling by a factor that they call the omega factor, which is a dimensional factor that values from 0 to 1. And when it's near 1, the canopy is not coupled to the atmosphere, or poorly coupled, uncoupled to the atmosphere. And the stomates, even if the stomates close, the transpiration doesn't decrease nearly as much because the canopy gets hotter, and the rate of transpiration compensates partly the closure of stomata. Now, on isolated trees, they are highly coupled to the atmosphere, and when the stomates of the leaves of the trees close, the tree transpiration also reduces itself by about the same proportion. So all these complicated issues translate in a summary that I have put in this one. So in a warmer and higher CO2 climate, the short, dense, smooth crops like rice or wheat, the crop coefficient will be roughly the same. Now, in isolated tree canopies, olive trees for instance, the crop coefficient would be less as the CO2 increases, less than what is today. And for mixed canopies like vines or hedgerows or row crops at high distances, there will be smaller declines in crop coefficients. So the three components are summarized, are supposed to change, probably higher ETO, but depending on the season, shorter ETO, uncertain precipitation, and similar or lower Kc. And the question is, how do we integrate all these factors to predict irrigation requirements under climate change? Well, the best way to do it right now is to use simulation models. Simulation models combine future climates with crop simulation to predict the behavior of crops under those future climate scenarios that the climatologists develop with the global circulation models. So we have done a small exercise for Central Asia in which we chose 3 20-year periods, 95 to 2014 as a current situation, then mid-century and late century 20-year periods, 2 emission scenarios, a moderate and the extreme scenario that everybody uses, the most extreme, to find out how bad the situation could be. And I want to point out that all these simulations are based on different tools and simulators, because there is a lot of limitations in climatic data, especially in areas like Central Asia. There's very little information, and to run some of the crop simulation models, you need access to daily weather data, for which you need simulators using existing data to simulate future data. So there is a lot of uncertainty on this. Anyway, we simulated the net irrigation requirements in the future, in middle of 21st century and the end of 21st century. And these are the results for maize, the net irrigation requirements in current and future scenarios, depending on whether we take a moderate emission or a maximum emission scenarios. You can see this would be the average. It's very similar for all scenarios. So there was hardly any change under the climatic conditions that we simulated for Central Asia in Tajikistan. In other crops that we tried, and the simulations indicated less net irrigation requirements in the future. So not much of a change after you integrate all these factors were detected for this particular case. Now, the advantage of these simulation models is that you can ask questions and explore different adaptation options. So one exploration we did with maize was to plant late than what the farmers plant right now, in order to avoid the summer heat when the ETO is maximum. When you simulate the future water requirements on a late sowing, you can see that there was a big decline in irrigation requirements by about 30%. So there is some optimism here that with adaptation measure, we might be able to reduce irrigation requirements. And this applies to all the semi-arid regions. And I would like to point out that if the climate is warming and the autumn would be warmer than it is, than it has been in the past, we should take advantage of the autumn season and try to avoid growing crops in the middle of the summer when the ETO is very high. So that can be explored with these models. So to summarize, my opinion, and this is just an opinion based on what is known today, is that the net irrigation requirements will not change drastically under climate change. Will be similar for herbaceous crops and will be for less for tree crops, but of course, all is depending on the rainfall. What would be the future rainfall is the big uncertainty, and not only in terms of amounts, which we know they will vary from year to year, but also in the patterns of distribution and the intensity of the events. But really, to me, this is a small issue relative to the main question looking at the future. The question is, would there be enough water? And this is what we have to prepare for under climate change. We need to learn how to better manage the water that we have now so that we are prepared in the future for more severe situations in terms of drought cycles or increased demand. And we also need to store as much water as possible, not only to have sufficient water for drought periods, but also to mitigate the problems of floods. We need to take a new look at the options of storing more water, including storing more water in the ground, it's groundwater. This is, to me, a challenge that should be associated with the efforts in improving climate change, because we know one thing for sure. In the present climate, we already have sufficient drought periods that are creating tension among users and within users. So the situation is bad enough so that if we prepare for a worse situation, we will be able to solve whatever problems arise from the changing climates in terms of irrigation water supply. Thank you.
Thank you, Professor Elias, for highlighting the effect of climate change, temperature increase on the crop development and growth cycle and the irrigation requirements. I'll now move to the second presentation of Dr. Dirk. Professor Dirk is an emeritus professor at Cww2022 University in Belgium. He's a specialist in evapotranspiration, soil water balances, irrigation water management, and crop water productivity. He closely cooperates with FAO in the development of the aqua crop software, which is FAO's crop water productivity model. Professor Dirk, the floor is yours, please.
Thank you.
Yes, we have 15.
Yes.
Thank you so much.
Hello? Can you hear me?
Yes, we do. Yes, we do.
Elias, I can hear you, but we don't know if Zoom 2, which is the host, is
But
able.
the presentation was okay? Could you hear?
Yeah, perfect.
Okay. No problem.
No.
Okay. So we'll wait. We don't know what. We wait for Zoom 2.
Mhm.
They should launch it. Okay. Yeah, thank you.
Dirk is supposed to talk now. So we should be seeing him.
I don't know. Probably they are
Yes.
going back to
Pasquale,
the
can you hear me?
To the audience.
use and then give
Elias, can you hear
Yeah.
me?
because he's there in person, we should be able fact to see the room like at the beginning.
Okay. Thank you. Thank you, Mr. Chairman. So what I would like to propose to you, to show to you, is how aquacrop simulate the water productivity under climate change. No, it does not work. Yeah. I point to there. Thank you. So we all know that transpiration consists of the vaporization of liquid water, which is transferred to the atmosphere through the stomata. And at the same time, when the crop transpires, it takes up CO2 through the same pathway, and then by photosynthesis, the crop produces carbohydrates, which are the building blocks for the biomass. So transpiration and CO2 uptake uses the same pathway, and that is presented in this linear relationship. There is a strong linear relationship between the transpiration and the CO2 uptake, or in other words, the biomass production. Now, this relationship is known as the water productivity, the biomass water productivity, and it gives you the slope of the line. It's expressed at kilogram biomass per square meter of soil surface per millimeter of water. So if the crop is well watered, the stomata are open, the crop can transpire a lot of water, take up a lot of CO2 and produce a lot of biomass. If the crop is water stressed, stomata are closed and also CO2 uptake is limited. Now this relationship is linear, but it is however specific for a specific climate and a planting date, and also for CO2 concentrations. Therefore, in aquacrop, we use the normalized water productivity, normalized for climate and normalized for CO2 concentration. So the normalization of climate consists in not considering the sum of the transpiration, but the transpiration divided by the reference evapotranspiration. It is a normalization by considering the evaporative demand. And the normalization for CO2 concentration consists in calculating this for one specific CO2 concentration, which is 369 parts per million, which is the CO2 concentration, or was the CO2 concentration, which was the CO2 concentration in the year 2000. So with this equation, where we multiply the normalized water productivity with the sum of the amount of water which was transpired throughout the season, normalized for water demand, for climate, you can calculate the biomass. Here you see an example for maize with data from China, Ghana, and other countries, and you can see that if you plot the data for normalizing it for the year 2000, they are all on the same line. Notwithstanding, these are different cultivars, different climates, different climates, different planting dates. Now, of course, the CO2 concentration is increasing. We all know that. Today we have already more than 400, and in the future we end up with more than 1,000 if you believe this negative, very pessimistic, sorry, story actually. Of course, there are other stories which are more moderate, but still result with a CO2 concentration of around 600. Now, how do we simulate that in aqua crop? So the change in the CO2 concentration, that is by multiplying the water productivity with an adjustment factor. An adjustment factor which consider crop type, because the C4 crop reacts differently than a C3 crop, but also by considering the CO2 concentration. Now, Steduto et al., they calculated actually how that adjustment factor will be, and they found that it is about 45% higher than under the conditions in the year 2000. So it means that the biomass production will be 45% higher due to that higher CO2 level. Now, Van Utrecht et al., they analyzed the phase experiments data, and they found that the correction factor is only 5%. So in a phase experiment, as you know, CO2 is blown over the fields, and if sensors sees that the CO2 concentration is too low, then more CO2 is blown in the field. So we have in aqua crop the possibility to either use the theoretical adjustment or the adjustment based on the phased experiments. With the help of a sync term, you can put it at 100 or 0% or any value between. Now lately, Allen et al., they analyzed the phase experiment again, and they show that the fluctuation of the CO2 concentration makes that the crop underreacts actually, or reacts lower than if the CO2 concentration is constant. So maybe the results from the phase experiment were not fully correct, and now it seems that the sink strength of 100% is more precise. So far we looked at the window up to 550 parts per million. If you go above, well, before there was no correction in aqua crop, and then of course whatever sink strength you use, you get crazy values for correction for CO2, which are of course not realistic, because it is well known that the crop responds not very strong anymore, starting at CO2 concentrations of 7. So we analyzed some data from Wageningen, and we found there that the correction levels up about 60%. Still with a warning that there is a lot of uncertainty. So, to conclude, if we look to the effect of climate change on crop production, there is an increase of the atmospheric CO2, which makes that the adjustment factor goes up, becomes larger than 1. That is the effect of CO2 fertilization. There is a warning, however. You can produce more biomass due to the CO2 fertilization, but the crop does not need only CO2, it needs also nutrients. So you need also to increase soil fertility. Otherwise, you cannot see the effect of the CO2 fertilization. Now, the atmospheric concentration increases, and as a result, air temperature, evapotranspiration, and also the rainfall pattern will change. As Elias mentioned, air temperature and evapotranspiration rises, rainfall varies a lot now, and there might be longer periods of longer dry periods. This will result in a negative effect because due to the more water stress, and then the summation of the transpiration, the corrected transpiration will be also less, resulting in less biomass. So with this equation, aqua crop can simulate the combined effect of the CO2 fertilization and of the altered weather conditions. And if it goes, the yield goes up or down, depend on the one hand on the crop, if it is a C4 or a C3, whoops, and it depends also, sorry, we lost the screen. So it depends on the crop type, C3 or C4, but also on irrigation and especially fertility management, as I would like to illustrate with an example as a conclusion. Okay, there we are back in business. So that is the example. That is a huge FAO project in West Africa. So there were 10 project sites, a few in the Sahelian zone in Niger. There were others in Gambia, in Mali, and also in the Sudanese zone in Côte d'Ivoire. There were different crops considered: tomato, rice, maize, and sorghum, irrigated and rain-fed, and everything was calibrated for the current management in aquacrop. Climatic data was collected, 10 regional climate models actually, and we generated with that climate data then the historical data that was for evaluating, of course, the model performance, and then also data for the year 2030 and 2050, well, for the horizon of 2030-2050, with two different RCPs, a pessimistic one and a moderate one. Here you see the results of the climate projection for the 3 best models. And as Elias was saying, precipitation is very unknown. We don't know so much. But what was analyzed here is that the variation from year to year seems to increase. So with the 3 models, it was an increase of 16%. Temperature by 3 degrees, that is, of course, for the pessimistic scenario in 2050, and ET naught by 8%. Then we simulated for the different crops irrigation strategies. They were, of course, also on different soil types. For the different climate conditions, we simulated what is the future yield, and we did that with 2 management options. One was with the current conditions. The current conditions where soil fertility is somewhat limiting. And if we see the results, these are the results of the relative yield change with reference to the baseline period today. And you see that they are negative. So the yield declines by 15% up to 20% for rain-fed crops, actually. So the light red is 2030 horizon, the darker red is for 2050. And that is because the crop cannot profit from that CO2 fertilization because soil fertility is limited. So that was then another simulation we did. So we increased now the soil fertility, and as a result, you can now see that the positive effect of climate change, the higher CO2, gives also a higher yield, especially for the irrigated crop, because there also water stress was limited. While for rain-fed crop, you can still see a positive effect for the rain-fed rice, not for maize, but that is because that is a C4 crop. We just not react very strongly on the CO2 fertilization. So as a conclusion, these are nice simulations, but there are always some limitations which you have to take into account, because that is not necessarily the reality. There are pests and diseases. None of the models, none of crop models simulate that. Heat stress is in aqua crop, but maybe not on all processes. The last one which I would like to mention is land degradation, which is not simulated by any model. And land degradation, that will be surely happen due to surface runoff of the high rainfall, which comes with change of climate. It was proven also this year. And also a lot of wind erosion, long periods of dry weather. And this result, of course, in loss of fertile soil. So your model can say, okay, the yields might increase thanks to that soil fertility, which was improved. We put it extra organic or inorganic fertilizers. There was fallowing or intercropping or other methods. But if you don't consider the loss of fertile soils by land degradation, then your results might be more optimistic than what is in the reality. I thank you.
Thank you, Dr. Dirk, for highlighting the results of the simulation of the water productivity under climate change. while highlighting the major limitations of those models. I'll now move to the third presentation, which is on the assessment of climate change impact on selected crops in the Arab region, which will be presented by Dr. Ihab Jnad. Dr. Jnad is the director of the Water Resources Department at the Arab Center for the Studies of Arid Zones and Dry Lands, ACSAT, in Damascus, in Syria. He is also an associate professor at the Faculty of Agriculture at Damascus University in Syria since 2001. He specializes in water resources management using mathematical modeling, impact assessments of climate change on water resources, and estimations of crop water requirements from satellite images. His areas of expertise also include rainwater harvesting and irrigation management. Dr. Ihab holds a PhD in water resources engineering from the University of Texas A&M in the United States of America. Thanks, Dr. Ihab, and the floor is yours.
Thank you. Usually I don't like this session after lunch because you will most of the time they are sleeping, but I see most people wake up. And thanks for thanks for Elias and Derek. Actually, they paved the way to my presentation. We'll see some application to what I mentioned. And I loved the last slide of Derek. I will. So first, let me talk a little bit about the projected climate change in our region. Of course, most of you know about the RECAR initiative, which this was maybe the first project makes the data available, climate change data available for our region with 50-kilometer resolution for different climate model. And according to this climate modeling, the rainfall in our region, we can see here. Yeah, we can see from the legend that the yellow and the brown, this area will have less rainfall, more dark brown. This means less rainfall will be, and the blue more rainfall. Unfortunately, the Arab region mostly have yellow and brown, and especially the Maghreb area. The Maghreb area, this is the most impacted area by climate change, and this is what we have seen. For temperature, we see all our region will have increase in temperature, in average about 3.7. This for the worst case scenario, but actually some area will have 5 degrees, like Mauritania and the neighbor country. Not only rainfall and temperature, the extreme event, like the maximum links and the drought event, all this, I mean, the maximum links to dry spell will be longer. You can see more frequent drought. We have result not published here. We can see more frequent and more intense drought in our region. So the question now, how this climate change will affect agriculture or the crop yield? The climate change will affect the crop yield through the change in temperature, precipitation, concentration of CO2, extreme event. Actually, we can see there is, as Elias and Derek mentioned, there is impact of temperature and precipitation. Most of the time, I will say, will be negative impact on the yield of a crop. But at the same time, we'll have CO2 has positive impact. So the outcome from both effects could be either way. Could be positive or negative, depend on the crop and on the change in temperature and precipitation. So really we don't know. Therefore we need modeling. So in order to assess the impact of climate, we have to use models because we need to link climate with the soil, with the crop. So there's no way to do this without modeling. And there is different growth model available. You can see here, DSAT, aquacrop, crop seeds, and maybe there are other models. But always, I mean, really, if we need to use a model, we need model has easy input, available input. less detailed input. And of course, aquacrop model developed by FAO, and we are pleased today to have Derek, Pasquale, Elias, the developer of aquacrop model, and really I would like to thank them for their support to our region. I mean, provide technical support. And main advantage of aquacrop is water-based model. Water-based model. This means there is direct relationship between the yield and the available water in the soil. And this is very important, especially when we want to develop deficit irrigation or water scarce area. Also, it has the potential to be used to assess the impact of climate change on a crop. The other model, one of major problem of aquacrop is used for only, cannot be used for tree crop. This is major disadvantage, and we always ask Derek, I mean, if there is future hope, I mean, to improve, so aquacrop will be able to be used for tree. So far, and we have, I am from ACSAD. I mean, ACSAD is a regional organization. We work in all Arab countries. We get a lot of questions about assessing the climate on citrus tree, olive tree, and date palm tree. So we cannot use aquacrop. So we start to look to other model to be used for a tree. And so one of these models is a crop cyst model developed by Washington State University, and can be used for vegetable, for cereal, and for the tree, but only the tree calibrated, the model was calibrated for. Still not all the tree. So for example, citrus, still we don't have data for calibration for, we cannot use crop cyst for citrus. We used here for apple tree, because it was calibrated for, and Washington State is, I mean, it's very famous for apple. And one of the problem of crop cyst is that there is not a lot of documentation and support available. Really, we faced a lot of difficulty to use this model, but I mean, through communication with Washington State University, and we got, but like aquacrop, it has a lot of material available, a lot of support. I mean, it's easy to learn. It's not the situation for the crop cyst. So what I will do, I will present two projects. I mean, actually, we used this model to assess the impact of climate change, and I'm pleased. I mean, some of the comment was already mentioned by the. So the first project, this recent now, which is almost finishing up this project with FAO and ESCWA. It was funded by SIDA, and the project title Increasing Watershed Resilience to Climate Change. This was applied in Algeria and Lebanon, two watersheds in Lebanon. Algeria, we applied on 3 crops: wheat, tomato, and potato. And even RICAR is available for the whole region. In Algeria, Tunisia, and maybe part of Morocco, they are within the European Cortex. Within the European, you can see this is a European Cortex. So the northern part of our region, part of Egypt also, and Lebanon, the whole Lebanon is in Euro Cortex. Of course, Euro Cortex has an advantage, is 12.5 kilometers, very good resolution, and it is bias corrected. I mean, very important when you want to use climate change data in impact study, it must be bias corrected. We cannot use, I mean, we can use for vulnerability study, non-bias, but not for impact study. So this data is bias corrected. And we can see in Algeria, there was, we used 5 models from Eurocortex, 5 climate model. So, I mean, the reduction rainfall range in this model, it's up to 100, I guess, 112 reduction in annual rainfall, 112 millimeter, a lot of reduction, I mean. And the wheat, first I will present the impact on wheat. Wheat is rain fed. This is very important because in the northern part of Algeria they have the wheat, and we are pleased to have we have our colleague from Algeria. They were part of this project. So always when I used aqua crop, I had this problem, and I had a lot of discussion with Elias and Derek about the CO2 impact. And I guess I explained there is still high uncertainty about the positive impact of CO2. So what we can do in this situation, I said, let's present always the result in two cases. One with considering impact of CO2, and one with considering, we don't consider the positive impact. In this case, you'll have range. So if you are a decision maker, maybe I will consider the worst case, that there is no positive, even if there, I mean, of course there is positive impact, we are sure, I mean. So if we take the output, the impact on yield without the positive impact of CO2, we can see the projected reduction in the yield of wheat, rain-fed wheat in this part of Algeria is about 22%. Of course, always when we talk about climate change, we have to talk about at least 3 models. In this case, we have 5 models because there is high uncertainty. So the average, this reduction, 22%. If we consider the positive impact of CO2, the reduction will be only about 10%. So we are in this range. I mean, we don't know really. I mean, if which one is correct, but we are in this range. So 22 is high reduction, especially when we have now this crisis with wheat availability and food security. 22%. This only due to climate change. We don't consider other, I mean, factors like fertilizer, water, and no water is considered, of course. And the impact of a growing cycle. This is what Elias mentioned, but here I will show exactly, because we have increase in temperature. The length of the growth cycle is linked to temperature directly. So we found the projected reduction in the growth cycle of wheat is 2 weeks. Of course, aqua crop does not simulate quality of the wheat. So this reduction in the length could have impact not only on the quantity, could impact the quality of wheat. Sorry, just we are advertising for FAO aqua crops. So if we look to the effect of climate change on the daily ET0, we can see there is increase. This is exactly what Elias mentioned on the daily. However, if we look on the seasonal, the whole season, because we have reduction of the growth cycle, the decrease in crop water requirement 17%. So actually, this could be positive impact of climate change. Most of people, they say we have climate change increase in water consumption. In fact, because we have less water, this will be less water used for irrigation. For tomato, I will do very quick. For irrigated crop in general, less impact. So when we consider the CO2, actually we have projected increase in the yield, and without considering the positive impact, we have 2.5% reduction. This is for the cycle, the reduction was 10 days. And this for water consumption. Yeah, I like this one. The heat stress, and what Elias mentioned in the last slide, I like it very much, that aqua crop that does not consider heat stress in all stage, which is very important for our region. This region has a lot of heat stress. And we can see here that the average temperature stress is increasing due to climate change, which could have, this will have negative impact on the, this for apple, we use the crop cyst model. And in this case, after we have the second phase of recap, let's say, there was modeling for the Mashriq area. Mashriq area, this is the domain, include Arab Peninsula, Lebanon, Syria, Palestine, Iraq. The climate model done with 10 kilometer resolution. Of course, everybody here, I would like to mention that the database for Mashriq and for Rika is available for anybody. Anybody can take, and this is a good opportunity to use this data in different study. So for apple, the projection was 47% when we don't consider the positive impact of climate, because apple, it requires certain number of frozen. So really the increase of temperature will have a lot of impact on apple. If we consider the positive impact, the reduction, I guess, is 26%, still high, even if we consider the positive impact of CO2. So really we have another project, we also with FAO, ESCWA, and supported by, funded by SIDA. We finished. There was different crop. Every country, they selected the main crop in this country. And I will go some result. Morocco, as I mentioned, the Maghreb area, this will have the highest impact. The projected reduction, 26%, very high projected. In Sudan, the sorghum reduction in yield about 11%. In Yemen, irrigated wheat, 7%. Most of the time, irrigated crop has less, impacted less with climate change. So, in summary, of course, we'll have negative impact, and it will be more on rain-fed wheat, and the crop growth cycle will be reduced, and this could affect the quality. And heat stress due to climate change is more pronounced in summer crop. We found it more in summer crops. What we can do, so this is a negative impact. Of course, we should start from now applying adaptation measure, and what I guess Riaz or Derek mentioned about the changing of sowing days. This is very important because there is shift in starting of rainfall, and we did this scenario on aqua crop. If we shift the sowing date by 1 month from 25 November to 25 December, we did this simulation. We found that there is an increase in the yield about 30% by just shifting the planting. This is very important for as adaptation measure. Of course, now we have a lot of variety developed by AXAD, by ICARDA, is heat resistance and resistant to drought. Of course, if we plant this, will be have less impact by climate change. Conservation agriculture, very important technique now start to be used in most of the country. It has 3 major components. With minimum tillage, with soil cover, and with rotation. We keep the water within the soil. We keep the organic matter within the soil and less CO2. Of course, it has. I was in Tunisia yesterday. I met with some farmers. They said impossible to apply conservation agriculture because it's very difficult to keep the plant residue. Nobody will leave it for second year, but maybe they have to do that in future. Of course, water harvesting is very important technique. At AXAD, we apply a lot, especially Hill Lake. Hill Lake, this technique is very, useful, proved, for farmers to provide water in dry period, for supplementary irrigation with minimum cost. There's different technique we found very helpful for adaptation to climate change. So if we not take action, climate change will threat the water and food security in our region. And thank you very much.
Thank you, Dr. Ihab, for the interesting presentation. I'll now give the floor to the audience for a few questions. We're going beyond time, so I hope that we will not be beyond time much. So, any question to our guests? So we have a question here. The mic. We cannot hear.
Anyway, you will probably hear my question. I don't know if the colleagues will hear it. I mean, there were three different presentations with the results that were not, I think, if I understood well, even though it was a bit sometimes a bit complex, but the results were not always consistent. So maybe can you try maybe to present some trends? I understood that depending on the type of crops, like low crops or high crops or with a high canopy, or C3, C4, the result could not be the same. So maybe could you, Dirk, or maybe the other colleagues, let's say maybe just give the trend for the main categories of crops, if that's feasible, if that's not oversimplified.
Well, I'm sure that also Pasquale and Elias, which are online, can maybe intervene. What I already can tell in aquacrop, we make indeed that adjustment factor which we use to consider the effect of increased, of elevated CO2. We make a distinction between C3 and C4 crops. Because it is well known that C4 crops like maize, like sorghum, does not react very much on an increase of CO2 because they have a more better cycle. They already use very good the CO2. While C3 crops, they respond very strongly actually on those on the CO2 concentration actually. Now, we don't make distinction in aquacrop between the different types of C3 crops. Although I remember that Eline van Utrecht did some ideas or launched some ideas that the sink term which we were mentioning, so that you can increase or decrease the effect of CO2 which we use in aquacrop, might be somewhat different in the future. For example, for roots and tubers like potato or sugar beets, they will react differently than a cereal crop. Cereal crops seems to react better than the roots and tuber crops. Although, well, I have to look more in that data, but there is, as mentioned, still a lot of uncertainty because, especially for the C4 crops, because C4 crops are not much studied in, for example, the phase experiments. And phase experiments are always with C3 crops, C4 crops, because they know they do not react very much, so there is not much study on it. So we don't have neither much data to say how strong or how weak a C4 crop will react.
Any other questions? Do we have online questions from the audience? Yes, sir, please.
Thank you very much, Dr. Ihab, and I agree with you for your recommendation for adaptation. I think to minimize tillage, we have to do more in these important topics with regard to consider no tillage, which will help only for improving the soil fertility, but also it could help for reducing the evaporation. And I think in this direction we have to concentrate more research in this important. We have to to move, because as you see everywhere we have shallow and deep blowing, which will be a good condition for erosion and so on. So I fully agree with your recommendation in this. Thank you.
Any more questions? Do we have an online question? Yes, please do. Isha. So we have an online question from one of our audience. Please go ahead and ask your question, please.
Thank you very much for giving the time. This is Dr. Imran Azam, climate change and water management expert from WWF Pakistan. And thank you very much for sharing wonderful presentation. My question is relating to sowing period especially. In one slide, expert was saying we can manage a maybe kind of temperature and period. If I say with reference to Pakistan, especially recent climatic conditions, we are in an Indus basin. Right now, we don't have enough water for the cropping period, second winter season cropping period. But 2 months before, downside of Pakistan observed huge rainfall. Heavy rainfall, more than 5.7% more than normal period. My question is, from the expert, kindly explain and just how can we manage the temperature, especially in this scenario? Thank you very much.
Yeah, manage temperature. So indeed, temperature increases the heat stresses of crops, and it also increase also evapotranspiration, as Elias was calculating actually. Now, how can you manage it? Of course, in open field it might be, I think, very difficult. What I've seen in greenhouses, that they spray actually water vapor each time the temperature goes too high, and then the water evaporates, and then the temperature becomes lower inside greenhouses. But that's of course in a controlled environment. In open field, yeah, you can sprinkle also water. Yes, maybe you can.
Yeah, always. I mean, sprinkler system. This one was the main advantage. I mean, then can adjust temperature, but we cannot do that in surface and drip.
Can I comment?
Yes, yes.
This is Elias Ferreres. I think the case of Pakistan illustrates that it might be better to manage water than temperature. If you can collect some of the excess water and store it underground or in more dams, then you would be able to use it when there is no water. And that, what happened in Pakistan recently, is an example. You know, you could also, if you had more dams and more capacity for storage, it would have been less flooding. Thank you.
Well, thank you. I think I'm sorry we've gone beyond time, so I'll give the floor to Dr. Muhammad Al-Hamdi for the concluding remarks. Still, we'll have a launch of our report on remote sensing ET following the conclusion of Dr. Al-Hamdi.
Thank you very much. Thank you, Muhammad, and sorry for those who had questions. Maybe they can address the speakers directly through email. Well, we've listened to the science, and basically I'm a little confused. On one hand, we promote the science policy interface, and we've heard a lot of science with a lot of messages, which to me seems a little bit difficult. Now, if I put myself in a policymaker shoes, he will really be very confused. So I think we really need to make efforts to try and interpret the messages coming from science in a simple language. I know in this case there is a lot of uncertainty, there is a lot of factors that enter into this, and it seems to me that science is not conclusive on it. And that's the nature of the climate change. There's a lot of uncertainty connected to it. Elias was giving us more of, well, productivity is not going to change much. Derek was saying yes, but we need to look at it will, but we need to look at soil fertility. So there is so many factors that are there, and of course I can imagine that this would be also site specific. What works in Morocco might not work in Sudan, etc. So there are difference in climate and topography, etc. So what I'm trying to reach is science is very important, and we need to look at it critically, and we need to develop that further. And I really appreciate the work that has been done with Aquacrop and the work that the whole group, and also what FAO headquarters is doing on this. But we need to simplify that into some simple messaging that our policy makers and our politicians can understand and take proper actions on the ground. If I was a decision maker today, I would be, I would not know what to do, basically. So, yes, I think that's an important message. Can we go back on the slide to the cover page of the report? I just want to introduce what we're also doing along these lines with the ET determination. We all know, before I do that, I would like to thank the speakers, Derek, Ihab, and Elias. Very much, I think what they presented is very useful and very innovative, and of course it's very scientific that we need to take into account when translating this into policies, but we need to understand it fully first. Now moving into the launch, Mohammed said launch, it's not really a launch, it's a pre-launch. We have a report that looks at the ET determination, the remote sensing ET determination, and here we're looking at the uncertainty and errors. This is the result of more than 20 webinars that has been conducted. And there is a lot of extensive work with lead scientists in this area that have contributed to this webinar series. Our colleague, our friend, Pasquale Statuto has gathered all of this. He was behind it to actually try and make sense of the uncertainty on how far can we rely on remote sensing as an emerging technology, as a cheap way of collecting data in order to determine ET. So with this, I give the floor to Pasquale. If you hear me, Pasquale, the floor is yours.
Thank you very much, Mohammed. Yes, I can hear, and I will share the screen now. Hoping that everything will work. Can you see it? Can you confirm that you can see the screen?
Yeah, it's coming. It's not yet, but it's coming.
No, it's coming. Okay. Tell me when it shows up. Nothing yet?
Yes, now we can see it, please.
Oh, okay. So, thank you very much, Mohammed, and I'm happy to be here. Sorry for this distance, but I couldn't do different. So, what we are doing, we are very happy for this pre-launching of the publication on remote sensing determination of evapotranspiration, looking at algorithm, strengths and weakness of the various models, uncertainty, and best fit for purpose. The report will be made available in the public domain in the coming weeks. The publication is an output of the Water Scarcity Initiative from the NENA region and supported by the SIDA project on water efficiency, productivity, and sustainability in the NENA region. It builds on outcomes of the webinar series on the same subject and expand on the most recent literature to provide the state of the art to the readers. Both the webinar series and the publication have unfolded because of the recent advance and development in the determination of evapotranspiration. As we know, evapotranspiration, or ET, represents nearly always the largest share of water outflow, which we define as a consumption from agricultural and other vegetated lands. So quantify ET in space and time is therefore extremely relevant for several purposes in water resource management, from national water accounting all the way to farm irrigation. Nevertheless, quantifying ET is a very demanding task, and particularly for large scale. The only feasible and affordable methods for ET determination are through satellite remote sensing, although this carries over several challenges. Thus, both the webinars, the series, and this publication have drawn the knowledge of the most world-class authority in the domain of remote sensing ET determination, along with the regional users and experts of the various models. Let me then provide you with the list of the names and faces of the authors of the publication. Here, I know we are out of time, so I will go very quickly. Just you can recognize most of them, from Rick Allen to Martha Anderson to Joshua Fisher, but also our colleague from the region, like Chandra and Ajit from Itarda, El Sheikh from our colleague from Sudan, and then the Chinese Academy of Science with El Bija, our colleague from headquarters, like Yipe, that is following one of the major projects, and then the various people from the European Space Agency, from the European Commission Earth Observation, from NASA, from the Dauteri Water for Food Institute, and several others, and like I said, also the Chinese Academy of Science. So I will not spend too much time in describing all of them, but you can see that these are the top people behind the remote sensing, especially in the latest years, the latest even, I would say, very recent years. So looking more into the content of the publication, we have an introduction that discusses the reasons why it is necessary to enter this new era of remote sensing determination of ET, what are the challenges users are facing, and how the publication trying to address them. Then a background section illustrates the major models of remote sensing ET that have demonstrated the highest significance and relevance for operational use at various scales. So the section recalls the basic theory behind the models, referring to the surface area balance, the Prissy-Taylor equations, and to the satellite psychrometric approach. The section also highlights the strength and weakness of the various models and their best fit for purpose. The remote sensing models that the publication addressed is CEBAL, the surface energy balance algorithm for land, metric, mapping ET at a high resolution with internalized calibration, Alexi with also the disaggregated component is Alexi, the atmosphere band exchange inverse, CBOP, the simplified surface energy balance operational, the Prissy-Taylor from the model from the Jet Propulsion Lab, ET Loop, ET Motor, and ET Watch. Also, the remote sensing models have generated some of the database and portals which differ from each other for spatial and temporal resolutions, geographical coverage, length of the time series, and other peculiarities. What we addressed and discussed in the publication is what you see here as the Fine Early Warning System network of the United States Geological Services with ET data from Cww. Then we have above the FAO Water Productivity Open Access Portal with the ET data from ET-Look. We have the Global Daily ET Loadet with ET data from Alexi and Alexi. EE-Flux, the Earth and G EE-Flux with ET data from Metric, and then the Open ET with the ET data from an ensemble of models. Basically, several models are put together to run and derive a combined evapotranspiration. Of course, as I said, also the geographical coverage difference among them, and the OpenET is still more for US and not yet arrived in other regions of the world. Then the publication also deals with the presents some of the application, field application, with the experience from the MENA region, like in the case of Iran, the Jordan, Syria, and Tunisia, that several experts have been using the various models in the field. Then another application that is presented is CIMIS, the Satellite Irrigation Management Support, that is used for essentially provide the actual crop coefficient through the NDVI to support irrigation scheduling. And this is done at 30-meter resolution. But also we have ERIWatch. ERIWatch, the CEO is Vilas Jansen. It is a sort of private business that provides estimates of soil moisture to drive irrigation scheduling. Of course, it's mostly meant for on-demand irrigation. It has a spatial resolution of 10 meters, and the soil moisture and the evapotranspiration are determined daily and provided to the farmer every morning. Then there is an extensive chapter dedicated to the uncertainty and accuracy of the ET determination, which represents how much of this uncertainty are acceptable for specific purposes and what can be done to reduce them, like using the CIMET procedure, which is a calibration using inverse modeling of extreme conditions. This section describes as well the various methods for assessing uncertainty and their propagation in the final results. The various ET model performance are also observed in different boundary conditions at different scale, and then there is a section dedicated to their intercomparison. Then the publication dedicates also a section on prospects for the near future, referring to the recent or new programs and missions. Among them, we have EcoStress, Ecosystem Spaceport Thermal Radiometer Experimental Space Station. This is from NASA Jet Propulsion Lab, which is tracking ET with a high resolution thermal radiometer, measuring the land surface temperature at 40 times 70 meters and temporal resolution directly in 1 and 5 days, depending on the actual orbit of the satellites. Then we have Copernicus. It is an EU Earth observation and monitoring program offering information services covering sphere, marine system, land system, climate change, and emergency domain. A peculiar aspect of the Copernicus program is the use of a satellite constellation indicated as the Sentinel-5. These satellites have sensors, some of them, these sensors with spatial resolution down to 10 meters and 5 days sensor. Then we have a FAO with Vapor Phase 2, which is an improved version of the passage of its look, with the integrated land surface sensor for enhanced soil moisture determination. And then we have Hydrosat, which is another private initiative planning to launch in 2024 a new constellation of satellites providing, among other data, the daily land surface temperature at 10 meters spatial resolution. So daily land surface temperature at 10 meters. So finally, and here I will close, the publication approaches the conclusion after providing a discussion with reflection on the lesson learned, insights on the subject matter, take-home message, and how to follow. The publication is also enriched with an extensive list of reference over 120, which provides the reader with a wealth of knowledge, further insights on the subject. Of course, I'm not going to preempt, let's say, the outcome of the discussion, the reflection, and the conclusion of the publication. We do not have any way of time, but invite everybody interested in the remote sensing determination of evapotranspiration to visit either the FAO publication website or the Water Scarcity Initiative website in the coming weeks to access and download this, what we think is a quite significant publication of the Water Scarcity Initiative program. And with this, I stop and thank you very much for your attention.
Thank you, Pasquale, for the presentation. And let me maybe say again that the reason we're preparing this report is not to question the modality of remote sensing. We think that the technology is there to stay. It's making things cheaper. However, we don't want to take it for granted. We want people who use it know what is behind it. They need to know the assumptions. They need to know the uncertainty that is connected with these applications that are coming, relying on the technology of remote sensing. That is the idea, and I think this is going to be an addition to a scientific addition to the field of remote sensing and ED determination. Thank you, Pasquale, and we all will be looking forward to the finalized final version of the report. Thank you all for being here and for attending this session. I think this has been very important session, and the discussions, I am sure, will continue in the future. So have a good evening. Thank you.